Most people walk past quartz that looks like diamond until they miss the $5,000 stone. In certain alluvial zones, a clear, sharp-edged crystal kicked aside by a boot could be more than just common quartz. The difference isn't in how it looks from a distance, but in what most people never test. True diamond rough doesn't always sparkle with brilliance. In the field, uncut diamonds often appear greasy, slightly dull, and may even resemble frosted glass rather than a showy gem. This deceptive plainness leads to major oversight, especially in regions where quartz is abundant and regularly weathered into crystal habit forms. The real opportunity lies in training the eye not to seek brilliance, but to recognize the subtle optical traits, crystal geometry, and feel in hand that distinguish the real from the lookalike. Rough diamond often forms as octahedra, 8 faces forming a double pyramid, though etching and erosion can obscure this shape. Quartz, by contrast, favors hexagonal prisms with a pointed end, and glass rarely forms any natural crystal shape at all. But in flood zones, where erosion and sediment redistribution bury and unearth rocks continuously, even worn quartz and glass can mimic the rounded contours of a diamond nugget. That's why a visual read is never enough. Weight is one early differentiator. In hand, a quartz crystal of equal size to a diamond will feel markedly lighter. Diamond-specific gravity is approximately 3.52, while quartz hovers around 2.65. That difference, while subtle, becomes intuitive with practice and side-by-side comparison. Even more revealing is the luster. A clean diamond fragment, especially when lightly wiped, reflects light in an almost oily or adamantine way, while quartz remains plainly vitreous. But this first glance, if passed over too quickly, costs real money. Field collectors in the Arkansas crater of Diamonds Park, the Namibian deserts, or parts of Canada's Northwest Territories have documented walkover finds later verified as multi-carat stones. These weren't dug from depth, but spotted near the surface, mixed with pebbles and detritus that looked no different to the untrained eye. Why are these missed? Because most assume the dazzling find will announce itself, but real diamonds in the field rarely do. They blend in, especially in sediment-heavy zones post-flood or excavation, and only stand out when inspected at close range with mental checklists. Is the shape octahedral or cubic? Does it resist scratching from quartz? Is there any hint of greasy luster? Once you've missed one, the loss lingers. But for those who know what to test next, the tools get simpler and sharper, and that's where most get misled by brilliance alone. Brilliance alone deceives, because quartz, glass, and even lab fakes all glitter in sunlight. The untrained eye is drawn to light bounce, mistaking surface sparkle for internal fire. But in gem identification, not all brilliance is equal. The key is knowing how and where that light behaves and why. Quartz and glass both exhibit what's known as vitreous luster. Under direct sunlight, they reflect light crisply off the surface but lack the depth and intensity of true diamond. Diamond exhibits adamantine luster, a deeper, oilier shine with high refractive behavior that creates multiple internal flashes from a single light source. To the trained eye, diamond's brilliance is sharper, faster, and more angular. But in rough form, especially when coated in dust or film, this brilliance is dulled, making visual inspection alone unreliable. Even skilled buyers have been fooled by well-cut glass or zircon stones set into low-value jewelry. This is because high-index glass simulants can mimic the flashiness of a well-cut diamond, especially under jewelry store lighting designed to enhance sparkle. But when these stones are removed from their settings and examined with a 10x loupe, their limitations become obvious. For example, a diamond under magnification reveals crisp, clean facet junctions and no bubbles. Glass, even high-end leaded variants, often shows gas bubbles, rounded facet edges, and poor symmetry. Quartz may show crystal inclusions or veils, but lacks the internal dispersion of light, what jewelers call fire, which separates real diamond from most fakes. Moissanite adds further confusion. It's the only widely used simulant that can match or exceed diamond in brilliance due to its very high refractive index, around 2.65 versus diamond's 2.42. But moissanite reveals itself through optical doubling. When viewed through a loupe, facet lines appear doubled, slightly blurred, or split. No natural diamond does this. Weight can also mislead. Some high-index synthetics are heavier than diamond. For example, zircon can mimic both look and heft, clocking in at a specific gravity of about 4.6, higher than diamond. Without side-by-side testing or proper instruments, A novice might mistake a heavier glass simulant for something rarer, or dismiss a lighter true diamond as quartz. So how do you know? It starts with isolating features beyond surface shine. Step 1 is to examine brilliance in varied lighting, not just direct sun. Try incandescent, diffuse daylight, and flashlight beam. Diamonds maintain angular flash under multiple angles. Glass and quartz typically fade or scatter. This is where tools begin to matter. A thermal conductivity tester, even an entry-level one, can break the illusion fast. So can a simple loupe and a willingness to slow down, because the next test isn't just about how it looks, it's about where it comes from. A glittering stone in your hand means nothing if the ground beneath it can't explain its presence. That's the pitfall most casual hunters fall into. They search where diamonds are unlikely to exist geologically, mistaking chance sparkle for local promise. But real diamonds have very specific birthplaces, and those places leave their own visible clues. Natural diamonds originate deep within the Earth's mantle, formed under extreme pressure and heat, then delivered to the surface through volcanic pipes. These pipes, composed of a rare rock called kimberlite and less commonly lamprite, serve as the primary transport mechanism. Without a kimberlite or lamprite host, or ancient glacial movement from such a source, there is virtually no geological reason for a diamond to appear. So how do you know if you're in a terrain where diamonds might be found? Look first for regions with known or suspected kimberlite pipes. In Canada, for instance, the Lac de Gras region contains dozens of economically viable pipes. In the US, the only public-access diamond-bearing site is the Crater of Diamonds in Arkansas, where eroded lamprite pipes have seeded the surrounding soil with loose diamonds. In southern Africa, from Botswana to Namibia, entire diamond economies rest on ancient riverbeds and coastal drift lines connected to deep-source volcanic activity. But terrain tells its own story. Kimberlite pipes often weather into soft, chalky soil that stains reddish or yellowish due to iron oxidation. You may also notice unusually circular depressions in satellite maps or even from ground view, indicative of collapsed volcanic conduits. The ground around these areas can host telltale plant patterns too. Certain vegetation avoids high magnesium soils common in ultramafic rocks like kimberlite. The importance of glacial drift cannot be overstated either. In much of Canada and the northern United States, glacial activity scoured kimberlite zones and transported diamond-bearing material far from its source. These erratic boulders and gravels, especially in eskers and drumlins, can conceal diamond indicator minerals even hundreds of kilometers from the original pipe. This is why tracing up ice from known finds remains a core exploration method. In regions without known pipes, terrain logic still helps. Ancient paleochannels, long-buried riverbeds, can serve as secondary reservoirs, particularly in Africa and South America. Diamonds liberated from kimberlite or lamprite by erosion settle into low-velocity zones like meander bends, back eddies, and gravel bars. Even in deserts like Namibia's Sperjebiet, diamonds are found not where they formed, but where they were concentrated by time and tide. That's why finding a shiny stone in a random creek bed means little unless the surrounding geology backs it up. But if you also find heavy minerals, magnetite, ilmenite, garnet, especially with rounded forms and deep coloration, the odds shift dramatically. These are your first breadcrumb clues that a deeper source may be nearby. Finding a single heavy mineral isn't enough, but spotting the right combination can change everything. Pyrope, garnet, ilmenite, chromite, and certain types of spinel don't just hint at diamonds, they mark the path toward their source. These indicator minerals survive erosion and transport, and their presence in stream sediments or till is the first serious sign that diamond-bearing kimberlite may be nearby. Start with pyrope garnet. This deep purple to reddish mineral forms under the same high-pressure conditions as diamonds. Not all garnets are equal. Almandine, common in metamorphic rocks, won't lead you to a pipe. Pyrope's color is typically more vivid and can be confirmed by refractive index or simple color comparison if you're trained. In the field, its high specific gravity means it concentrates in the same sieved fraction as gold or magnetite, heavies in the pan. Ilmenite is another major signal. With a dark metallic luster and strong magnetism, ilmenite often appears in black sand concentrates. It's slightly magnetic, stronger than garnet, weaker than magnetite, and can be teased out using a rare earth magnet across your pan residue. Its presence, especially alongside pyrope, strengthens the likelihood of kimberlite proximity. Chromite adds to the case. Though common in ultramafic rocks, the variety associated with kimberlite has distinct compositions that geochemical labs can verify. In the field, its black, submetallic appearance and very high density allow you to isolate it during panning or sluicing. A rounded, well-formed chromite grain, particularly if not associated with serpentinized peridotite, warrants further testing. Clinopyroxene and spinel may also show up in the same heavy fractions. These are more advanced indicators but follow similar rules. Only certain chemistries, low aluminum, high chromium, or magnesium, match diamond-stable zones. Without a lab, these distinctions are speculative, but the fact that multiple indicators show up together is not. To extract and assess these, you'll need a standard field kit. Sieves down to 40-0, 425, a gold pan or batte, and a good magnet. Begin by panning down to black sands from suspected terrain, gravel bars near old volcanic zones, glacial tills, or river bends in craton regions. Dry sieving followed by wet concentration narrows the material. Then sweep with a magnet. First, remove strongly magnetic magnetite. What's left may include weakly magnetic ilmenite, non-magnetic garnet, and denser grains worth inspecting under a loupe. Finding 2 or more of these in a single concentrate, especially garnet and ilmenite together, justifies a deeper look. Professionals grid the area, sample systematically, and track upstream to source. At this stage, a map, GPS, and careful tagging of sample sites matter more than any one crystal. Processing field material isn't just digging and hoping, it's a deliberate method to isolate meaning from the dirt. When diamonds don't announce themselves directly, their signature comes from what travels with them. That's where sieving and panning for heavies becomes your most efficient early filter, converting a chaotic pile of gravel into a structured mineral readout. Begin with site selection. Choose a zone where heavy minerals can accumulate naturally. Inside river meanders, behind large boulders, or in low-energy gravel beds, these are ideal sediment traps. In glacial till, look for spots where meltwater has sorted material. And in dry terrains, dry washes and ephemeral streambeds mimic similar logic after storms. Use a classifier stack starting at 20 mesh, about 0.85 and descending to 40 around 0.425. Most kimberlite indicator minerals, including garnet, ilmenite, and chromite, tend to concentrate in this size range, which balances visibility with practicality. Any material finer than 40 becomes difficult to identify reliably without lab tools, while coarser material may exclude the most diagnostic grains. Once classified, pan or sluice the material. A shallow batte pan works best for visualizing color contrast among heavies, but standard gold pans are perfectly serviceable. Swirl gently, allowing lighter quartz and feldspar to wash off while the dense grains settle into the riffles or bottom crease. What remains should be black sand magnetite, deep red to purple grains garnet, metallic blacks or bronzes ilmenite chromite, and occasional greenish fragments, pyroxenes or serpentinized material. Next, introduce a magnet test. Sweep a neodymium magnet wrapped in a plastic bag or taped inside a vial across the concentrate. Strongly magnetic grains like magnetite will jump. Ilmenite responds sluggishly or not at all, depending on grain orientation. This step clears bulk interference and allows better inspection of the remaining non-magnetic material. At this point, place your concentrate under a 10x loupe or field microscope. Identify garnet grains by their color. Pyrope garnets show deep wine red to violet and occasionally dodecahedral crystal shapes. Ilmenite appears metallic, jet black, and may show a faint metallic sheen when rotated. Chromite is similar but denser, duller, and may display submetallic to resinous luster. These are your prime suspects. But even this process has traps. Zircon can sneak in small, high-luster grains that mimic garnet or chromite in weight and color. Likewise, glassy fragments from human activity, cullet, sometimes appear in older alluvial systems. Sorting through this requires not just technique but comparative memory. Each session improves your identification reflex. To track progress and build certainty, sample methodically. Mark each pan location with GPS or grid coordinates. Take note of how many grains of each type occur per pan. A single garnet may be a fluke. A pattern multiple garnets accompanied by ilmenite or chromite signals a potential upstream source worth pursuing. Don't discard the non-diamond material too hastily either. While not valuable on their own, these indicators may lead you directly to the source, especially if you trace them up gradient and start seeing concentrations spike. That's how major kimberlite pipes have been discovered in Canada and Africa, one garnet at a time, then a trail, then a pipe. The second test often complicates more than it confirms. A pan full of promising garnet and ilmenite can stir hope, but when the density test reveals something off, it forces a sobering reassessment. That's because even dense, sparkly minerals can fall short of diamond's very specific gravity, and failing this benchmark is often the first real filter that cuts false positives down. The specific gravity (Sg) of diamond is about 3.52. It's higher than quartz 2.65, slightly above most common rocks and noticeably denser than glass. In hand, this density difference is subtle but trainable. Seasoned fieldworkers develop a weight intuition after enough side-by-side comparisons. But for most people, the difference becomes obvious only when tested in water. The classic method is water displacement. Start by weighing the suspect stone dry, ideally with a digital scale to the nearest hundredth of a gram. Then suspend it in water without touching the bottom or sides of the container, using a fine mesh or thin thread to minimize water tension errors. The increase in weight represents the buoyant force. From that, Sg equals dry weight, wet weight. If the result lands significantly below 3.5, you're not holding a diamond. Quartz, even in dense clusters or crystal form, will produce values closer to 2, 6, 2, 7. Zircon and sphene may flirt with 4, 0, 4, 7, confusing the hopeful, but their other traits, optical doubling, fluorescence, or luster, eventually betray them. Moissanite, often touted as a near match, registers between 3.2 and 3.3, close enough to confuse but just low enough to flag a caution. This test often dispels early excitement. Even a crystal that passes the visual and luster checks can sink expectations here. Field testers routinely find high-index glass or dense spinel simulants that sparkle convincingly but sink below the 3.5 threshold. And because diamond rough is often irregular or partially embedded in matrix, even slight variations in test setup can skew results. That's why repeatability is crucial. Test the same specimen multiple times and always with a known control stone if possible. Sometimes results land on the edge, 3.48, 3.49, that's when it gets tricky. Impurities, microscopic inclusions, or surface cavities can slightly alter readings. This is where density testing overlaps with judgment. If every other indicator is strong, a borderline result isn't a disqualifier but a flag for further tests. Field kits now often include thermal testers to resolve such ambiguity, but even before getting technical, the weight in water test is a powerful eliminator. It doesn't prove diamond, but it narrows the field to candidates worth further scrutiny, and it protects you from chasing quartz shards or spending money to lab test a worthless crystal. Thermal conductivity separates diamonds from nearly every lookalike, but even this test has its blind spots. A small handheld device no bigger than a pen can pierce through sparkle and weight to measure how fast a stone pulls heat from its tip. Real diamond dissipates heat so efficiently that it fools the tester into silence or delivers a sharp diamond beep. But moissanite, diamond's closest rival, can trigger the same result, and that's where most buyers and field hunters get caught off guard. Thermal testers work by pressing a heated metal probe against the stone's surface and measuring how quickly the heat is drawn away. Diamond is an exceptional thermal conductor, outpacing all other gemstones by a wide margin. Even corundum, sapphire, and ruby lags far behind. That's why this test became a standard tool in jewelry shops and pawn counters. It delivers instant feedback, is non-destructive, and works on mounted or loose stones. In the field, a thermal tester is small enough to carry and run on batteries. Use it only on clean, dry surfaces. Moisture or dust can interfere with readings. Press gently against a flat facet or smooth face of the stone. If the device confirms diamond, you've got a potential winner, but don't stop there. Because moissanite, a silicon carbide gem, also conducts heat rapidly, older thermal testers can't tell them apart. This creates a dangerous false positive, especially for rough or unset stones. To counter this, newer models include dual-mode testing, combining thermal and electrical conductivity. Unlike diamond, moissanite is a decent electrical conductor, while diamond is nearly insulating. That's the telltale split. If a stone conducts both heat and electricity, it's moissanite, not diamond. But beware, some diamond simulants, particularly coated synthetics or advanced glass, may mimic surface conductivity with enough residue or wear. And very small diamonds, under 0.02 carats, sometimes fail thermal tests simply because the surface area isn't sufficient for consistent readings. That's why testers recommend multiple probes or confirming with another device. One smart approach is to carry a confirmed diamond and moissanite sample as a reference set. Before testing unknowns, probe each control stone to verify the tool's behavior. This reduces error in varying temperatures or altitudes, common in remote prospecting regions. But the greatest advantage of thermal testing is speed. In a single hour, a field worker can screen dozens of suspected crystals, isolating only those that merit more detailed inspection. It removes 90% of false targets, quartz, zircon, glass, with minimal effort. It also pairs well with density testing. If a stone passes both, your odds climb steeply. It scratches glass, so it must be a diamond. That single phrase has led more people astray than any other in gem identification. Because while diamond is indeed the hardest natural material, it's far from the only one that can score a line across glass. Quartz, corundum, moissanite, zircon all can leave visible scratches. Some fakes are even designed to do exactly that. The glass scratch test, once a common standard, now serves more as a cautionary tale than a reliable indicator. The Mohs scale of hardness measures scratch resistance, not toughness, density, or value. Glass sits around 5.5 on that scale. Quartz at 7 scratches it easily. So does most synthetic cubic zirconia. Corundum, ruby, and sapphire ranks at 9, just below diamond's 10. Moissanite comes in at about 9.25. All of these will gouge glass without a second thought. The key difference lies not in if they scratch glass, but in how they behave under magnification. That's where the loupe test earns its place. Under 10x magnification, a genuine diamond reveals razor-sharp facet edges with no rounding. The meet points where facets intersect are crisp, exact, and carry no signs of melting or polish drag. Glass fakes, even high lead content diamond simulant varieties, will display slightly rounded edges, sometimes visibly chipped or abraded. The polished lines may appear irregular or blurred. These defects, barely visible to the naked eye, betray their identity under close inspection. Another trait is the facet count. Diamonds, especially brilliant cuts, follow strict geometry, 58 facets in a standard round cut. Simulants often diverge slightly, using simplified cuts that look flashy but lack precision. Even rough stones show telltale differences. Diamond rough, especially octahedral, tends to exhibit natural cleavage planes with stepped or triangular growth marks. Glass or quartz fakes, by contrast, show conchoidal fracture, curved, shell-like surfaces, typical of amorphous materials. In some cases, artisans intentionally shape glass to mimic rough diamond. These can include etched lines, frosted textures, or embedded bubbles to replicate inclusion patterns. But real diamonds do not contain trapped gas bubbles, only natural inclusions like small crystals or clouds. A single bubble under the loupe disqualifies the specimen. There's also the facet doubling effect, a diagnostic feature for moissanite. Under magnification, look for doubled or blurred facet lines, especially when viewed through the crown at an angle. No natural diamond will show this. It's a subtle but powerful test to distinguish between the two hardest contenders. One low-tech trick is to breathe on the stone. Diamond disperses heat so efficiently that fog vanishes almost instantly, within 1 second. Glass or quartz will hold fog for 3 to 5 seconds. It's not definitive, but it complements other observations. The combination of these small tests, hardness, loupe edge quality, fog, facet count, builds a diagnostic picture. Each may be inconclusive on its own, but together they eliminate nearly every non-diamond candidate. Still, there's one stone that continues to mimic diamond through every basic test, and it doesn't break under pressure. In fact, it behaves almost identically. The moment a stone passes visual, scratch, density, and thermal conductivity checks, confidence surges. But then it fails the electrical test, and the entire case collapses. What you're holding, most likely, is moissanite, the most convincing diamond simulant ever engineered, and the reason experienced gem buyers always run one more test before sealing the deal. Moissanite, or silicon carbide, was first discovered in meteorite fragments but now exists almost entirely as a synthetic product. It has remarkable properties: a hardness of 9.25 on the Mohs scale, higher brilliance than diamond, and thermal conductivity that can match or even exceed real diamond. On paper, it checks nearly every box. That's why many thermal testers alone will falsely register moissanite as diamond. creating a false positive that can mislead even cautious prospectors or jewelers. The giveaway lies in electrical conductivity. Diamond is an electrical insulator. It doesn't conduct electricity under normal conditions. Moissanite, on the other hand, conducts electricity to a measurable degree. Dual-mode testers combine both thermal and electrical sensors. When a stone passes thermal but conducts electricity, the tester flags moissanite and not diamond. In practice, this difference becomes critical at the buying stage. A 1-carat moissanite may retail for $300–500. A diamond of identical size and appearance can fetch $4,000–7,000 depending on clarity and cut. That delta is where fraud thrives. Without the electrical component in your tester, or without performing the test at all, a moissanite can enter the market falsely labeled, unintentionally or by deception. In the field, identifying moissanite is even harder because most of the telltale traits, facet doubling, color under LED lighting, slightly greenish tinge, are subtle and inconsistent in rough form. Some lab-grown moissanites are deliberately cut to mimic diamond's octahedral rough habit. Others are coated or heat-treated to alter their visual performance. This means that even a rough crystal showing diamond-like shape and luster, when isolated by sieving and passing density and thermal checks, could still be moissanite. One workaround in the field is to carry a portable electrical probe tester. They're more expensive than thermal-only devices, but provide critical verification in remote areas. Alternatively, back at a lab or trading center, you can use advanced instruments like Raman spectroscopy or infrared absorption, but these are beyond most casual hunters' access. The moissanite trap underscores a deeper lesson. A single test is never enough. Even a suite of consistent results must be interpreted in context. What's the terrain? Are the accompanying indicator minerals right? Is there a chain of evidence that supports a natural diamond's presence here? When that chain breaks, even slightly, confidence should fall, not rise. Because while moissanite is a marvel of materials science, it's not a diamond. And if you mistake one for the other, the market won't be kind. Even when every field test says diamond, a final invisible layer of doubt lingers, because some diamonds, despite being chemically and physically identical to natural ones, are made in a lab. These lab-grown diamonds now enter the market in rough form, indistinguishable by weight, brilliance, hardness, or conductivity. And while they're real diamonds by every material standard, they don't carry the geological history or the market value of a naturally formed stone. This is the limit of field testing, and where lab analysis becomes the only truth teller. Lab-grown diamonds, whether produced by high-pressure, high-temperature HPHT or chemical vapor deposition CVD, are flooding the gemstone market. They're atom-for-atom carbon crystals exhibiting identical physical and optical traits. They pass every scratch test, every density test, and every thermal and electrical check. In rough form, they even mimic natural growth habits. Some show octahedral forms or stepped cubic faces. Without specialized instruments, a prospector in the field cannot distinguish a lab-grown diamond from a mined one. Why does it matter? Because the premium in the diamond market comes from rarity, not just substance. A 1-carat natural diamond might retail for $5,000. The same lab-grown stone, visually identical, could sell for $1,000 or less, and continues to depreciate as supply grows. For buyers, provenance isn't just preference, it's price protection. So how do you know what you have? In the field, you don't, but gemological labs do. Institutions like GIA, IGI, and HRD use advanced tools, photoluminescence spectroscopy, UV absorption, and microscopic growth pattern analysis to detect subtle clues. For example, CVD diamonds often show strained patterns under cross-polarized light or distinctive fluorescence under shortwave UV. HPHT stones may contain metallic inclusions or growth zoning not seen in natural crystals. These labs can also detect treatments, clarity enhancements, fracture fillings, or color irradiation that alter a stone's appearance without affecting its basic chemistry. That's why professional buyers and auction houses won't accept rough or cut stones above a certain size without lab verification. And that's where the ethical and legal line sharpens. Misrepresenting a lab-grown stone as natural is considered fraud in many jurisdictions, even if the material itself is diamond. For field hunters, this raises a dilemma. If a rough diamond-like crystal passes all in-field tests, the only responsible next step is to document the find, preserve its context, and submit it for certification. Keep photos of the site, GPS coordinates, indicator minerals, and the recovery process. All of this builds a chain of custody that supports natural origin, essential when dealing with high-value stones. This also highlights the role of context. Lab-grown diamonds don't occur in indicator-rich gravels, behind boulders in meandering streams, or eroded from kimberlite pipes. If your stone came out of a coherent sediment trap, accompanied by garnet and chromite, and matches the terrain's geological story, the odds of it being natural rise significantly. But you still need the lab to close the case. When a single stone can't tell the full story, patterns in the land become your best evidence. Professional exploration teams don't rely on luck or lone crystals. They follow grids, trace indicator mineral trails, and apply repeatable sampling logic to prove whether a location is genuinely diamond-bearing. It's not about finding a diamond. It's about showing that the terrain can produce them consistently and naturally. This approach starts with systematic sampling. Once you've isolated a promising site, say a stream bend with garnet and ilmenite, you don't just keep digging randomly. You establish a grid. Use flag markers, GPS coordinates, and physical reference points like trees or boulders to define a search matrix. Sample at consistent intervals, every 10 or 20 meters depending on terrain, and process each sample separately. The goal is to map indicator mineral density spatially and spot where concentrations spike. This spike often indicates proximity to a source. In glaciated terrains like northern Canada, the method involves tracing indicator minerals up ice, against the flow of past glacial movement. Each sample with a higher density of pyrope, garnet, or chromite means you're getting closer to where the ice scraped over a kimberlite pipe. The process is forensic, incremental, and grounded in centuries of geological drift mapping. In fluvial environments, it's about water flow and sediment energy. Heavy minerals sink fast, so you're looking for gravel traps on the inside of river bends, in crevices behind obstructions, or at points where gradient flattens. These natural traps concentrate heavies. If you find multiple indicator minerals across several adjacent pans, the evidence begins to stack. It's no longer just a lucky pan, it's a vector. Field teams use multiple mesh sizes in each sample course for rough crystals, fine for small indicator grains. They may run samples through a wet shaking table or heavy liquid separation to get cleaner concentrates. In areas with known pipes, they also check for blue ground, the decomposed surface layer of kimberlite, which may contain altered olivine, serpentine, or magnetite clusters. Sample logs matter. Each concentrate gets labeled, bagged, and recorded. Observations like color zoning in garnet, magnetic response, and grain shape, angular V's rounded, feed into a wider dataset. Rounded grains suggest distance from source. Angular grains may mean you're right on top of it. Even negative samples help. If indicator minerals drop off sharply in one direction, you've bounded the target. Teams then triangulate the likely source zone, sometimes within tens of meters, a resolution fine enough to justify test drilling or trenching. This methodical approach has led to the discovery of major kimberlite fields in Canada, Angola, and Russia, often after years of patient grid sampling. For solo hunters, this might seem excessive, but even basic version of this workflow, tracking garnet counts per pan, mapping positions, repeating over time, adds massive value to your find. It shifts the story from "I found a diamond" to "this terrain has a diamond signal." That's the level where labs, buyers, or exploration companies begin to listen.